Early 1945, off the coast of Japan, an American F4U Corsair crash-landed in the Pacific after an engine failure during combat. The pilot ejected as the fighter hit the icy water. Within hours, Japanese patrol boats surrounded the wreckage. What they found would become one of the most valuable intelligence discoveries of the war's final months. For almost 3 years, Japanese pilots had faced this American fighter across the skies of the Solomon Islands, Rabaul, the Philippines, and now Japan itself. They had come to respect its speed, firepower, and seemingly indestructible build. But never before had they captured one in near-perfect condition, a chance to study, measure, and finally understand how far behind they had fallen. The story of Japan's encounter with the Corsair isn't just about a captured plane. It's the moment a nation's engineers came face to face with the full scale of American industrial and technological superiority. Through the Corsair, Japanese aviation experts would uncover hard truths about precision manufacturing, materials, and design philosophy that reshaped their view of their own abilities. The Corsair represented the peak of American fighter design. Created in 1938 to meet the U.S. Navy's demanding specs, it evolved from a daring concept into one of the most feared aircraft of World War II. Its inverted gull wing, huge Pratt & Whitney R2800 double wasp engine, and unmatched performance made it instantly recognizable. More importantly, it struck the perfect balance between speed, firepower, range, and strength, something Japan's aircraft industry struggled to achieve. The Corsair's story began in 1938, when the Navy's Bureau of Aeronautics issued a challenge: design a fighter that could exceed 400 mph in level flight. At a time when most fighters barely reached 350 mph, this was revolutionary. The Navy wanted more than just speed. It wanted a complete package: low stall speed for carrier operations, 1,000-mile range, heavy guns, and the ability to carry bombs. Chance Vaught's response was bold. Chief designer Rex Beisel and his team built their plane around the most powerful engine available, the Pratt & Whitney R2800 Double Wasp, an 18-cylinder, 2-row radial engine producing 2,000 horsepower, nearly twice that of most fighters at the time. To handle that power, they designed a massive 13-foot 4-inch propeller, the largest ever fitted to a fighter. The problem? Keeping enough ground clearance for that propeller while still making the aircraft suitable for carrier use. The solution gave the Corsair its signature look. Instead of straight wings, Beisel's team angled them downward from the fuselage before leveling out, creating an inverted gull wing. This design allowed shorter, sturdier landing gear and enough propeller clearance. It also reduced aerodynamic drag, improving performance. The prototype XF4U-1 made its first flight on May 29, 1940, with test pilot Lyman Bullard, Jr. at the controls in Stratford, Connecticut. On October 1st of that year, it reached a record 405 mph with tailwind assistance, the first single-engine American fighter to break the 400 mph mark. Its true top speed in level flight was 378 mph at 23,500 feet, still remarkable for its time. Production Corsairs reached frontline units in late 1942. The 1st Combat-Ready Squadron, Marine Fighter Squadron 124, deployed to Henderson Field on Guadalcanal in February 1943. The Corsair's debut wasn't smooth. On February 14th, during the St. Valentine's Day massacre, American forces suffered heavy losses, 9 aircraft down, including 2 Corsairs. The Japanese lost only 1-0. The 9-to-1 loss ratio forced U.S. commanders to halt daylight bombing missions until new tactics were developed. Pilots quickly learned that technology alone couldn't win battles. Tactics mattered. The Corsair wasn't built for tight dogfights. It excelled at boom and zoom tactics. Instead of turning with enemy fighters, pilots used its speed and climb rate to dive, strike, and escape before opponents could react. On May 13, 1943, 2nd Lieutenant Kenneth A. Walsh became the first Corsair ace, mastering these tactics and eventually claiming 21 victories. By 1943 and 1944, the Corsair's reputation soared. Operating from rough island airstrips, Marine squadrons used its toughness to devastating effect. It could take hits that would have destroyed lighter Japanese aircraft. Armed with 650 caliber Browning machine guns, 4 with 400 rounds each and 2 with 375, it unleashed massive firepower. Later versions swapped the machine guns for 420mm cannons, though many pilots preferred the heavier ammunition capacity of the 50s. the Corsair also proved versatile. By mid-1944, it was carrying 1,000-pound bombs, 5-inch rockets, and napalm canisters for ground attack missions. During the 1945 Okinawa campaign, Corsairs flew thousands of close air support missions, earning the nickname Angels of Okinawa from grateful troops. But Japanese pilots only saw part of the picture. From their cockpits, they faced a faster, tougher, deadlier opponent, but they couldn't know why it was so effective. Understanding that required hands-on analysis, and Japan had two top research centers for such work: the Yokosuka Naval Air Technical Arsenal near Tokyo, and the Army Aviation Technical Research Institute at Tachikawa. Throughout the war, these facilities had studied captured Allied aircraft, often wrecks salvaged from battlefields. But the recovered Corsair in early 1945 was different. It was almost fully intact. The Yokosuka facility, a massive research complex employing thousands of engineers and technicians, received the aircraft for detailed study. Despite saltwater damage, the Corsair structure was mostly intact, and its engine could be restored for examination. For the first time, Japan's top engineers could see the craftsmanship and design choices up close. They began with detailed photography and measurements, realizing they were studying not just a machine, but a blueprint of American innovation. Every dimension of the captured Corsair was carefully recorded. A wingspan of 40 feet 11.7 inches, a length of 33 feet 4 inches, and a height of 15 feet with wings extended, or 16 feet 2.3 inches when folded for carrier storage. The inverted gull wing design immediately caught Japanese engineers' attention. They understood its aerodynamic and structural advantages, but also recognized how difficult it was to build. The compound curves and precise angles required advanced tools and quality control, capabilities most Japanese factories could no longer maintain reliably by this stage of the war. One discovery especially surprised the technical team. Despite its advanced design, parts of the Corsair's outer wings were covered in fabric rather than metal. Specifically, the sections behind the main wing spar and around the gun bays. The ailerons, elevators, and rudder were also fabric covered. At first, this seemed outdated. By 1944-45, most modern fighters were all metal. But further analysis revealed the genius behind the choice. The fabric covering, a specially treated material, reduced weight in low-stress areas, saving valuable aluminum for critical components. Properly applied, it was strong, weatherproof, and far lighter than metal, a smart example of resource optimization. When engineers disassembled the wings, they found construction techniques that impressed and troubled them. The main wing spar, the key structural element carrying flight loads, was a massive high-quality forging. American metallurgy had produced aluminum alloys with strength far beyond what Japanese facilities could match. The spar's size and load capacity exceeded anything seen in Japanese fighters. It showed a crucial difference. The U.S. could produce large, complex forgings with consistent quality, while Japan had to rely on smaller, built-up assemblies that were less efficient and weaker. The internal wing structure showed the same precision. Each rib, stamped from aluminum sheet, was identical to the next, proof of strict manufacturing control. In contrast, Japanese aircraft built later in the war often showed variation between components due to rushed production and poor quality control. Attention then turned to the Corsair's armament. Its 6 Browning A&M 250 caliber machine guns, 3 in each wing, represented formidable firepower. The system was compact, reliable, and easy to service. Japanese examiners were impressed not only by the guns themselves, but by how well the entire system was integrated, from ammunition feeds and ejection ports to charging handles and access panels. The Brownings were masterpieces of precision manufacturing, the result of decades of refinement and mass production. Japan's own weapons industry simply couldn't match the reliability or consistency achieved by American factories. The team also noted 150 pounds of armor plate protecting the cockpit and a 1.5-inch bullet-resistant glass panel behind the windscreen, clear signs of American priorities. Japanese fighters, including the famous Zero, had largely abandoned armor to save weight and maintain maneuverability. That approach worked early in the war but proved deadly once U.S. fighters grew faster and more powerful. The Corsair showed that with enough engine power, like that of its massive R-2800, heavy protection didn't have to mean poor performance. The engine itself became the centerpiece of the analysis. The Pratt & Whitney R2800 Double Wasp was the pinnacle of American engine design, 18 cylinders in 2 rows of 9, displacing 20,800 cubic inches, and generating over 2,000 horsepower. It was a masterpiece of precision engineering. Though Japanese engineers had seen damaged examples before, this was their first chance to examine one in near operational condition. Inside, the craftsmanship was astonishing. Cylinders were machined to tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshafts had flawless finishes and perfect alignment. The 2-stage supercharger system, critical for maintaining power at high altitude, featured complex internal channels and precisely fitted moving parts, the kind of manufacturing accuracy Japan's factories struggled to achieve. Japanese attempts to create comparable superchargers had largely failed because of those limitations. Even more impressive was the engine's reliability. American radial engines routinely delivered full power for hundreds of hours between overhauls. Japanese engines often failed to reach their rated output and needed frequent repairs. The R2800's consistency came from superior metallurgy, better lubricants, tighter tolerances, and advanced quality control, all backed by an industrial base Japan could not rival. The propeller system told a similar story. The Hamilton Standard Hydromatic Propeller, 13 feet 4 inches in diameter with variable pitch blades, showcased cutting-edge aerodynamic and hydraulic engineering. Japanese designers understood the theory, but lacked the equipment and precision manufacturing to produce such large, perfectly balanced propellers. Every system revealed the same pattern: complexity executed with precision. The landing gear was intricate yet flawlessly built. The cockpit instrument panel featured a full array of gauges and switches far beyond those in Japanese fighters. The fuel tanks were self-sealing, made of layered rubber compounds that expanded when punctured, a life-saving innovation largely absent in Japanese aircraft. The electrical wiring was neatly organized, properly insulated, and clearly labeled, small details that spoke to overall quality. The more they examined, the clearer the truth became. Every part of the Corsair, and from major structures to the smallest bolts, showed uniform quality. Aluminum alloys were consistent, steel parts were heat-treated correctly, and surfaces were smooth and expertly finished. The aircraft felt solid, durable, built for long-term service. By 1945, Japanese production couldn't compare. Material shortages forced the use of inferior substitutes, aluminum quality had declined, skilled workers had been drafted, and factories operated under constant bombardment. Quantity had replaced quality. As Japan faced inevitable defeat, with B-29 bombers destroying its cities, the Navy shattered at Leyte Gulf, the Philippines lost, and Okinawa under siege, the Corsair's examination carried a somber weight. This was no longer intelligence gathering for future use. It was a painful acknowledgement of industrial reality. Engineers at Yokosuka and Tachikawa completed detailed reports on their findings, measurements, materials, and evaluations of American production. The tone was professional, but the message was unmistakable. In nearly every category, American technology surpassed Japan's. The gap wasn't a small one that could be closed with effort. It was the result of years of research, vast industrial investment, advanced supply chains, and a level of manufacturing sophistication Japan simply did not possess. By the end of the war in August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests that Japanese engineers managed to repair at least one of them, as photos show Corsairs with patched wings and fuselages. Whether any of these aircraft were actually flown remains uncertain, but the repair efforts make it clear that Japan was serious about trying to restore them for testing and evaluation. When American occupation troops arrived at the Yokosuka Naval Air Technical Arsenal in September 1945, they discovered clear evidence of extensive Japanese intelligence work. Captured Allied aircraft were scattered across the facility. Detailed reports, engineering drawings, and photographs documented Japan's efforts to analyze and understand Allied technology. U.S. intelligence teams quickly gathered these materials, recognizing their value for understanding how much Japan had learned during the war. The story of Japan's study of the F4U Corsair goes far beyond simple intelligence gathering. It represents the enormous divide between American and Japanese aviation by the war's end. When the Corsair first appeared in 1943, Japanese Zero pilots could still compete effectively through superior tactics and flying skill, but by 1945, even experienced Japanese pilots in newer aircraft had little chance against a well-flown Corsair. Its unmatched speed, power, and toughness, combined with overwhelming American numbers and better-trained pilots, made the odds impossible. The Corsair achieved an astonishing kill ratio of 11-1 against Japanese aircraft. American pilots flying Corsairs destroyed 2,140 enemy planes, while losing only 189 Corsairs to enemy fire. These numbers reflected more than the Corsair's technical excellence. They represented the power of the entire American war machine. Advanced technology, massive production capacity, efficient logistics, and consistent pilot training. Japanese engineers examining the captured Corsair understood this reality all too well. They could measure the performance gap, see the difference in manufacturing quality, and calculate the industrial imbalance. Their detailed reports served as sober acknowledgments of Japan's failed attempt to match the U.S. in technological and industrial might. The Corsair's story didn't end with World War II. The fighter went on to serve for decades, fighting in the Korean War from 1950 to 1953, where it excelled in ground attack and close air support roles even as jet fighters took over the skies. Foreign air forces, including France, flew Corsairs in colonial conflicts into the 1960s. The aircraft's final combat appearance came during the brief soccer war between Honduras and El Salvador in July 1969. On July 17th, Honduran Captain Fernando Soto, flying an F4U Corsair, shot down 3 Salvadoran planes, including 2 Corsairs, marking the last air victories ever achieved by the type. Ironically, the Corsair's final kills were against its own kind. From its first flight in 1940 to its last combat nearly 30 years later, the Corsair proved to be one of the most successful and long-lived fighters in aviation history. For Japan, its wartime encounter with the Corsair became part of a deeper post-war reckoning. After surrender, Japanese engineers and scientists, many of whom had struggled under wartime shortages, began working alongside American occupation authorities to rebuild their nation's industries. The lessons they had learned from studying American technology, including the Corsair, helped lay the foundation for Japan's future. The post-war Japanese commitment to precision, quality, and continuous improvement, traits that would later define its industrial success, can be traced in part to these wartime lessons. The captured Corsair recovered in early 1945 was more than just a downed fighter. It was physical proof of what advanced engineering, organized production, and industrial resources could accomplish. The lessons it offered came too late to change the outcome of the war, but they shaped the peace that followed. In studying the Corsair, Japanese engineers came face to face with the full scale of the challenge they had been up against. They had fought bravely and skillfully, but courage alone could not overcome the enormous technological and industrial advantages of the United States. The story ends not with triumph but with understanding. The Japanese technical reports on the Corsair, later recovered by U.S. occupation forces and now preserved in archives, remain silent witnesses to a moment when one nation's engineers confronted the reality of another's superiority. The captured Corsair itself is long gone, likely scrapped in the chaotic years after the war, but its legacy endures in the lessons it taught about how technology, when supported by resources, science, and disciplined manufacturing, can shape the course of history. Japan's aviation industry would rise again in the post-war years, stronger, wiser, and deeply aware of what true industrial power required. The 1945 examination of the F4U Corsair marked a turning point, the moment Japan's engineers fully understood the technological gulf that had opened during the war. It was a revelation written not in words but in aluminum alloys, precision forgings, and flawless craftsmanship, a powerful testament to the true scale of American industrial might.